In number 34, we are to use the rational zeros theorem to write a list of the zero candidates and determine which, if any, of those candidates are actual zeros. So our first step, as required by the directions, is to, and actually required by the theorem they're telling us to use, is to list our candidates. And remember, the candidates come from the factors of the constant, and the constant here is negative 14, over the factors, in fact I'm going to use ditto marks there, factors of the leading coefficient 3. So you will always write them as a list this way. And I don't really like using an equal sign because that's not really a mathematical statement, so we're going to put a colon there. Alright, so, and let me give you a little tip here. And 14 is not that big of a number, but this is a strategy that I recommend you adopt, and it will keep your thinking cleaner and clearer and save you some time. You're going to always list 1, so put plus or minus 1, comma. And what would you multiply 1 by to get 14? Obviously that would be 14. I'm not sure I'm leaving enough room here, so I'm going to slide down a little bit and put plus or minus 14 there. Alright, and then the next factor, you check 2. 2 works, so we're going to put plus or minus 2, and then we're going to put plus or minus 7, because that's what 2 would multiply by. Well, conveniently enough, 3 does not go into 14, 4 does not go into 14, 5 doesn't, 6 doesn't, so our list is complete for the top. And then the bottom is just plus or minus 1, plus or minus 3, because 3 is prime. So then we convert that into a list. That is not our list. That is where our list comes from. So we're going to convert that into a list at the end. So draw a little implies arrow, please. And here we go. So your first candidate is plus or minus 1, because plus or minus 1 divided by plus or minus 1 is plus or minus 1. So then there's not really a right or wrong way to do the list, but this is what I do. I do plus or minus 1 over plus or minus 3, which would be plus or minus 1/3. And then go to 2. So it's plus or minus 2, because that's over 1. And then plus or minus 2 over 3. And then our next candidate at the top was 7, so that's plus or minus 7. And then plus or minus 7 over 3. And then we have one more set to go, and that is plus or minus 14, and then plus or minus 14 over 3. Now that's a long list, but we are working from a calculator problem here, so let's pull in a picture to see if we can narrow this list down. So here's my picture. Now, what you need to notice about my picture, and you may have graphed it on your calculator as well, in that split second since we made that list, but if you want to, you can pause your video and actually graph this. But I zoomed this in for a reason, because in standard view, you'll get a very different looking picture. And please notice that we have a scale on the x-axis of 1/2, so that means we'd have 1 here, and then this would be 2 here, and this would be let me draw a little arrow there. That would be 2.5. And then our y scale is by 4s. And the reason I did that is that when you graph, if all you see is what looks like almost a slanted line, when it's a polynomial, you need to zoom out and make sure you can account for the extrema and the zeros. Now remember, this is a cubic, so at most it's going to have 2 extrema, and there's an extrema right there. There's a local max there and a local min there. And we could debate whether those, but that's where that's going to happen if we've got them. There's only 1 0 for this one, and it's right there. So it's somewhere between 2 and 2.5. So now we can look at our list with a new perspective here. So we're going to cross off anything that is not between 2 and 2.5. Well, 1 is obviously not. And since it's positive, we don't even need to worry about the negatives. So we know it's the positive version of whichever one of these numbers is between 2 and 2.5. 1/3 is obviously not. 2 is obviously not. 2/3 is obviously not. Cross off 7. Oh, wait a minute. Here we go. Here's our candidate, and it's 7/3, because obviously these two would not work either. So we're going to try 7/3. Now, you could do two things here. Once you've narrowed it down to 7/3, you can either use the remainder theorem, or you can use, or the factor theorem, or you can just simply use synthetic division. Now, I'm going to recommend here that synthetic division is going to work because your option otherwise is to plug 7/3 into f of x, which is what the factor theorem requires. So watch how easy this one works out. We have 7/3 as our outside number, and we have 3 as our first coefficient, -7 as our next, 6 as our next, and then a constant of -14. So put our bar, put the 3 down. Well, if I multiply 7/3 by 3, the 3's cancel and give me 7. If I add those, I get 0. If I multiply that, I get 0. If I add that, I get 6. And then I have maybe a little arithmetic to do here on the side. That's 7/3. I don't know why I was writing 2/3. 7/3 times 6/1. That's going to cancel to 2, which is going to give me 14, which confirms that our only 0 is 7/3. And so 7/3 is the only 0 from the list. On to number 46. And this one they gave you a picture. This is a no calculator problem. They want you to work strictly from the picture they gave you. And we are to use the upper and lower bound test to determine whether there are zeros outside this window. And this is a handy trick too to keep from zooming out and back and forth and trying to find the perfect window when you're trying to even if you're letting the calculator find the zeros for you. All right, so here we go. Let's start with upper because it's easier to work with. Well, in this picture, it's pretty clear that the curve does not intersect at 1. So wherever this intersection point is, wherever the 0 is, it's before 1. So let's try 1 as our upper bound. So make yourself a note. We're going to look at this as a candidate as an upper bound. So you put a 1 outside, and then we put our coefficients in order, and they are 1, -1, 21, 19, and -3. Put your bar, 1 down, multiply by 1, that's 1, that gives you 0. Multiply up, that gives you 0. Add, you get 21. Multiply, you get 21 plus 19, which is 40. Multiply up, you get 40. And add, and you get 37. And remember, the upper bound test says that if this row is all non-negative, and it is, implies that that 1 is an upper bound. Okay, so we've just confirmed that 1 is an upper bound. Now that tells us there are no zeros to the right of this picture. All right, then for our lower bound, we're going to do the same thing, but come over here to the opposite side, and that -2 looks a little too close, so I would use the -3, because it just needs to be below where I'm looking at the 0. Same set of numbers, 1, -1, 21, 19, and -3. Bring your 1 down, multiply up, add, you get -4. Multiply up, you get 12. Add, you get 33. Multiply up, you get -99. Gives you -80. Multiply up, you get 240. And that gives you 237 when we add there. And remember, the lower bound test says that if you alternate non-negative, non-negative and non-positive, it's a lower bound. Well, let's look. 1 is non-negative, -4 is non-positive, 33 is non-negative, -80 is non-positive, and 237 is non-negative. So we just determined that -3 is a lower bound. So that tells you there are no other zeros. So we could say no zeros outside the window. And that's the end of this video.